Good evening, chemistry kids. For the next to the last installment on average atomic mass, we're going to take a little side trip in these two parts into the world of nuclear physics and discuss why exactly the masses of isotopes aren't exactly equal to the mass number. And it's kind of a fascinating topic, how when an atom gets together, the weight of the atom is actually less than the weight of all the parts. So let's look into it. Some things to remember that we've discussed before. The nucleus is made of two parts, the positive protons and the neutral neutrons. So collectively we are going to call these nucleons. And this term will show up later in the PowerPoint, but just remember that it's equal to the two particles in the nucleus, and it's essentially the same as the mass number. Let's also consider some facts about the nucleus. We know, a la Rutherford, that the nucleus is very small and very dense. We also know, kind of common knowledge, that opposite charges attract and like charges repel. So this presents us with a bit of a problem. How can a nucleus, which is very small, stay together if it contains like positive charges, all those protons, in a very small space? This statement right here should tell us that all of those positive protons should want to try and get away from each other. When you say opposites attract and like charges repel, you're actually restating what is known as the electrostatic force, and it is one of the four fundamental forces that govern all matter. The other three are gravity, the nuclear strong force, and the nuclear weak force. We're going to focus in only on the electrostatic force and the nuclear strong force because those are the two forces at work inside of the nucleus of the atom. The nuclear strong force is the other force, and it actually causes protons to be attracted to neutrons. And as its name implies, the nuclear strong force is the strongest of the four. However, it's kind of like the sprinter on the track team. He may be the fastest guy, but he only works well over very short distances. Since it is the strongest, at least in the short distance, it can overcome the repulsive force of the electrostatic. So here's a picture of a nucleus here. We have all of these protons that, because of the electrostatic force, are repelled by each other. However, there is another force, the strong force, that is making these protons attracted to the neutrons. And at least over very short distances, it can overcome the repulsion for the like charges, holding the nucleus together if these two forces are in balance. Since these two forces are opposing each other, you got the electrostatic force trying to break the atom apart, and you have the strong force trying to pull it in tight. There's going to be an optimum range of protons and neutrons to keep this stable, sort of Goldilocks situation here where it's just right. Too many protons and you've got too many like charges, so the electrostatic force takes over, breaks the atom up. Too many neutrons and you've got the opposite situation. Too much strong force pulling that nucleus in tight. Both of these cause radioactive decay. Now this is not something that I would assess, but just to give some examples here so you know what I'm talking about, I'll give an example of each. Let me make that a little easier to see. In this case, we have a very large number of protons. Uranium atom has 92 of them. It's very big. So it has lots of protons, so lots of repulsion. The other strike against it is it's simply just a very large nucleus to begin with, 238 protons and neutrons. So it's so large that basically the strong force can't reach to the other side of it to hold it together since it only works over short distances. Because of that, it decays by releasing an alpha particle. Remember those from Rutherford? This is how they're made. Put uranium in a box and you'll get them. And when an alpha particle is released, it's basically two neutrons and two protons. So a new atom is formed with 4 lower in the mass number and 2 lower in the atomic number, so it's a different element. And this process is trying to bring it back down into a range where you've got closer to the ideal number of protons and neutrons. It's not there yet, by the way. This isotope of thorium is radioactive also, and it would continue to decay by other means, but besides the point. Let's look at an example of beta decay. Here's carbon-14. You may have heard of this when it comes to carbon-14 dating. It has an unusually high number of neutrons for a carbon atom. Most carbon atoms have a mass of 12, so this one has 8 neutrons instead of the normal 6. So too many neutrons, we've got too much strong force going on here. It makes it unstable. So what it does is one of those neutrons, which pretty much have all the quarks and subatomic particles to make both a proton and an electron, one of those 8 neutrons turns into a proton. So we go from 6 protons to 7 protons and ejects all of the parts to make an electron. And of course, when we change the number of protons, we also get a different element. So this is an example of beta decay as well. Moving on. So this Goldilocks range is a ratio of neutrons to protons of 1 to 1.5. So you can see here list of isotopes, and you can see this line has a slope of 1.5 and this line has a 1.1. If they fall within this range, they are likely to be stable. Also note, like we were talking about with uranium, no nucleus with more than 92 protons is stable. They're simply too large for the strong force to be able to reach all the way across the nucleus. So we're going to close it up here and pick up at this point in the second PowerPoint because it's going to be where the math picks up, and I just wanted to have that as a separate entity. So talk to you guys later.